Hello, everyone. Thank you for giving me the opportunity to present my keynote speech at the third International Conference of Biomedical Materials. My name is Abdul Rashid Alao, and I will be giving a topic on fatigue behavior of state-of-the-art dental ceramics, an overview. Okay, traditionally, metals are the materials used in dentistry to replace missing tooth or fracture tooth or fractured teeth in dentistry. And the types of methods that are used include nickel, palladium, cobalt, gold, titanium, and silver amalgam. However, because you can see from the picture, metals are opaque, that is, they don't have the color of the teeth. So, in order to improve the aesthetics of metals, they are often fused with glass, and that the name of the glass is porcelain. However, there are some side effects that when metals are used as dental restoration, they have the possibility that if two dissimilar metals are used, like gold and silver amalgam, one of them will become cathode, another one will be anode, and there will be transfer of electron through the saliva, which acts as electrolyte. So electrolysis will take place. So this one will lead to mouth battery, which is known as oral galvanism, which can cause intraoral cancer. Some patients are also allergic to metals. And another reason why this one is no more commonly used is because of the the chipping of the porcelain due to the mismatch in the elastic moduli of metals and porcelain. So that one can lead to porcelain fracture. Okay, now because of that, research has now changed into all ceramic materials, and these are the common ceramic materials that are used. The list is not exhaustive. However, we still have some materials that are being developed. So we have prismatic porcelain, we have mica glass ceramics, we have aluminum-based ceramics, lithium disilicate glass ceramics, white tetragona, zirconia polycrystal. So the two lithium disilicate glass ceramics and white tetragona zirconia polycrystals are the state-of-the-art dental ceramics that are commonly used because the lithium disilicate glass ceramic has got the highest strength among the glass ceramics, and also white rare tetragona zirconia polycrystals is the strongest among the dental ceramics for now. Now, this slide shows the practical application of manufacturing engineering in dentistry. So you can see the concept is computer-aided design, computer-aided manufacturing. So this one is used to manufacture dental restorations. When a patient has a dental caries like this or a fractured tooth, so it needs to be replaced. So the patient will visit a dentist. The dentist will use a scanner to generate digital image. That digital image of the affected part will now be converted using the software like SolidWorks or AutoCAD or design software to make the design of the affected area. Then the software will now, the software also has the capability to convert the design into a set of instructions that will drive the manufacturing of the restoration. That is known as computer-aided manufacturing. And this one we carry out in a desktop CNC like this. So these are the cutting tools. They call them in dentistry dental burs, B-U-R. Then it will now fabricate. This is a typical dental ceramics will be mounted like this, and then will now be fabricated. Okay, now the two materials that are the two state-of-the-art the dental ceramics are zirconia and lithium disilicate. So for zirconia, these are the microstructure of presintered and sintered one. Uh, for presintered, these are the components. It consists of zirconia, yttria, hafnia, alumina, and this one is carried out by compaction of all these particles and also isostatic pressing to get a green structure like this. So this green structure will now be presented at some temperature below 1000 degrees. That's why we call it presintered. So this is a microstructure that you can see some isolated pores, and you can see some interconnected pores. So the porosity is around 50%. When this presintered zirconia is now sintered in a typical furnace to 1400, 1450 degrees centigrade for 2 hours at 10 degrees centigrade per minute heating rate and the cooling rate. The grain size, because of the enlargement of the grain size, it will now cover close the porosity, and then the grain size will improve. Okay, you can see from 0.3 to 0.5, the porosity has reduced drastically, and the biaxial strength has improved, and fracture toughness also will improve. So CAD/CAM machining of presintered zirconia compared to sintered zirconia, for presintered zirconia, it is easier to machine. Then there is no phase transformation there. However, it comes with a price, which is extensive machining damage. There will be crack even the pores there are initiation site for cracks. Because of that, there will be strength degradation and the shortened lifetime of the restoration produced. For zirconia, it can be machined, but using high and expensive precision machinery that is known as ductile mold machining process. But there is a possibility that the phase can transform from tetragonal to monoclinic. Then it is also susceptible to aging, in which case, when there is a phase transformation and in humid environment, the fluid will exacerbate the transformation and also will lead to pulling out of the grains. That is known as aging. This can also lead to surface and subsurface damage, leading to strength degradation, reduced lifespan of the restoration, and also the cutting tool wear is also common because of the hardness of sintered zirconia. Now, for lithium disilicate, we have two also. One is for lithium disilicate, it can also be processed by using two structure. One is known as precrystallized lithium disilicate, which is known as lithium metasilicate, and it comprises of silica, lithium, potassium, phosphorus oxide, zirconia, zinc oxide. So they use the process of glass when they eat in a glass batch. Then from there, ceramic will also the ceramic material will also initiate from there. That is the lithium metasilicate. However, the grain size is very small. The grain size of the crystals, like lithium metasilicate crystals, is very small, and also biaxial strength and fracture toughness. When this material is now sintered to 850 degrees centigrade for 10 minutes at this heating and cooling rate, the grain size will improve, and also the biaxial and the fracture toughness of the material will improve. So the dental restoration can be processed using the tool. There you can see the pros and cons of the two. When you process the dental restoration using lithium metasilicate, it is very easier to machine because it is very soft. Then because of the softness and the low strength, there is a possibility that there will be surface and subsurface damage, leading to strength degradation and shortened lifetime. For lithium disilicate, it is also can be processed using high and expensive precision machinery. Then it is very hard. So by machining it by using hard machining, it can lead to surface and subsurface damage, which can lead to strength degradation, reduced lifespan, and also tool wear of the cutting tool. Now let me give you an overview of conventional fatigue. Fatigue generally is just the initiation, coalescence, and propagation of crack under applied loads. So that load can be static, dynamic, or cyclic. Static fatigue deals with the application of stress and strain, constant stress and strain. But dynamic deals with the application of stress and strain at a constant rate. Where cyclic fatigue leads to the fluctuation of stresses and strain, or what is known as oscillatory stresses and strain. And then fatigue can be done by using tension test, flexural test, shear test, torsion test, compression test. So what we now get from the fatigue is known as the SN curve, the stress and the number of cycles plot. So you can see three characteristics here. One is the useful parameters are why we perform fatigue tests to determine the useful parameter, which are fatigue life and fatigue limit. Fatigue life is the maximum load that the material, the maximum number of stresses, that the material can absorb before it fails. While the fatigue limit tells us the stress level below which the fatigue failure will not occur. So among all this is only A that has got fatigue life, but B does not have a fatigue limit. A has got a fatigue limit, B does not have. Then C, it doesn't have a well-defined cracking system. Now, the intraoral activities can be simulated by using the axial contact fatigue. Whenever a dental restoration is made, there is a need to understand the fatigue life and fatigue limit. So this one can also be simulated using axial contact fatigue. So you can see it is better to characterize failure mechanism in relation to contact conditions. It simulates oral loading conditions, contact load and indental radius. The contact load represents the biting force, where the indental radius represents the cost path. So what are the types of cracking system? One is cone crack. Cone crack, it initiates outside the contact cycle, where the axial tensile stress is maximum, leading to shipping. So this one the crack can propagate this way, then this one can be shipped up. Then quasi-plastic damage. This one initiates below the contact, where the maximum shear stress in the axial near field exceeds half of the yield strength. This one can lead to micro crack, coalescence, and damage accumulation. The other one and most dangerous crack is the radial crack. This one pops in from the starting floors when the maximum tensile stress equals the bulk flexural strength. This one can lead to the loss of strength. So in the literature, these are the parameters you can use to get the maximum maximum load for cone cracking, maximum load for plastic yield, maximum load to initiate radial crack. So this one for the critical load for the cone crack is a relationship between the fracture toughness, radius of the dental, and the ceramic modulus. For the critical load for the quasi-plastic is a function of the hardness, the radius of the dental, and the ceramic radius. For the radial crack, it's a function of the stress, okay, the maximum stress, and the ratio of the moduli of ceramic and substrate. So this one can represent the configuration of our enamel dental system. And the substrate can be a polymer. So, and that one can be a compliant polymer. It can be, that's why we simulate the dental. Then core will be enamel. That is the hard structure. That's what can represent dental ceramics. So, and if the ceramics is opaque, it needs to be veneered with porcelain. So, and these are the cracking system. Now, our aim is to fabricate, okay, high quality dental restoration for high reliability. So high quality fabrication from the CAD/CAM machining, then high reliability from the fatigue behavior. So these are the aims. These aims are to fabricate with CAD/CAM and investigate the machining responses, to subject the machine surfaces to different surface modifications, introducing uncontrolled floor density to investigate the surface integrity of the treated surfaces. Then for the fatigue behavior, to investigate the surface quality influence on the fatigue behavior, to unravel the prevailing failure modes. So this is the experimental design. You can see I started with lithium metasilicate glass ceramics, which is the one from the industry. Then these are the processes. One, some of them are CAD/CAM milled. Some after the CAD/CAM milling, some underwent polishing, some sintering, then some polishing, sintering, some polishing, sintering, glazing. Then some after the CAD/CAM milling, followed by sintering, glazing, some sintering, polishing. So we want to see which process can give the best or minimum surface roughness. So these are the cutting tools used in dentistry. This one is they call them dental balls. This one is step. This one is cylindrical. So the two are were mounted like this inside a desktop computer numerical control machine, CNC. So this is the SCM used to measure the surface roughness. You can see this is the machining surface. The surfaces were measured across, okay, perpendicular to the machine surface. You can see the machine surface, and this is how the profile of the measurements. So three places were taken, and the average surface roughness and the maximum surface roughness were carried out. So XRD result shows that the lithium metasilicate is the main crystals for the first material. When this one is polished and sintered, the sintering process has changed, converted the lithium metasilicate crystals to lithium disilicate crystals. Also, for sintering and glazing is still lithium disilicate crystals. So these are the roughness parameters, okay, of treated surfaces. You can see for the CAD-CAM, it has got the highest surface roughness, average surface roughness, and the highest maximum roughness of the peak and the value within an evaluation length, that is RZ. So polishing reduces the surface roughness. Then sintering after and glazing after polishing, after a milling, after CAD-CAM, also reduces the surface roughness. However, sintering after CAD-CAM reduces it. Then CAD-CAM sintered polishing after the sintering process does not significantly reduce the surface roughness. Then CAD-CAM polish sintered reduces the surface roughness, whereas CAD-CAM polish sintered glaze also does not significantly, glazing does not significantly reduce the polishing. Does not really reduce the sintering process here. So I used one-way ANOVA in order to understand how the effect of the fabrication process on the average surface roughness. So you can see when the p-value is less than 0.05, that means the fabrication process has got strong effect on it. So I also use PRT test to find out the effect of the one fabrication process on the other. So, and these are the results. You can see for the CAD-CAM mill versus CAD-CAM polished, you can see for the two surfaces, the polishing really affected the milling process. The same thing also for sintering. Here, sintering process after polishing significantly reduces the surface roughness. However, glazing after sintering does not reduce the surface roughness. So also is the glazing after sintering. So the two are not affected. So we move on to morphology in order to see the analysis clearly. So this one represents the machining grooves, which is due to pulverized surface. And this one causes surface defect. Then when this material was polished after milling, there is an abrasive wear, wearing of the surface, reducing the surface roughness. Then when it was further sintered, then there is a smooth surface due to defect healing. However, sintering after the CAD-CAM milling makes the surface to bulge. And then polishing after heat, we just do what? It leads to smearing grooves on it. Then also glazing after the sintering leads to the formation of powdered debris. However, glazing after sintering does not significantly improve the surface roughness. That is the surface morphologies. Now, based on this method, based on this engineering analytical engineering analysis, we came up with the proposed fabrication process for the fabrication of lithium disilicate glass ceramic. So the CAD-CAM milling must first be done. Then on the surface, on the occluser, that is the functional surface, facial and lingual surfaces. And this is the way an interglow surface where it will be bonded with adhesive. So once it is CAD-CAM milled, then needs to be polished. Okay, then after polishing, then sintering. This one will lead to a smooth surface on the surface. However, the interglow surface needs to be roughened. So CAD-CAM milling followed by sintering will roughen the surface for easy adhesion with dentine or substrate. Now, in order to determine the reliability of the test, so we carried out axial fatigue test, and this is the experimental setup. You can see this is the conditioned surface, and this is the spherical indenter, and they are mounted like this on a universal testing machine, UTM. And these are the experimental conditions. You can see the indenter radius, the radius of the indenter. The cyclic load fluctuates from 50 Newton to 800 Newton. The number of cycles, 100 to 10, 1, 10, 100, 1000, 3000. So we use high load, okay, low cycle. That one we mimic grinding of food. That is called bruising. Then the frequency applied was this, and this one leads to cyclic time of this. So we also use optical microscope and then SEM for surface morphologies. So this is how we formed the optical microscope. Once this is how we form the contact. The stress or maximum contact stress is governed by this equation. So this contact radius, the contact radius is formed this way. After the experiment, we took the optical microscope picture, then we draw about 4 lines, find the length of the line and divide by how many. So we have 1, 2, 3, 4. So we have about 8 radii there. Okay, this is 1, 2, so 8 radii. So we divide by 8 in order to get A. So, and also for us to use this equation, it means that the maximum contact stress must be lower than equals to 0.4 of the Vickers hardness of the indenter. So in this case, we use tungsten carbide. So the Vickers hardness of tungsten carbide is 20. So multiplied by 0.4 is equals to 8 gigapascal. So the maximum contact stress must be lower than 8. So according to this, we can see the maximum contact stress, none of it is greater than 8. This is the maximum, here is 6. So you can see for the proposed process, that is CAD-CAM polished sinter, you can see it is here we're at 1 number of cycle, but as when the number of cycles increases, you can see the only one that survived the 3000 3000 cycles here. So that means the fatigue resistance of the proposed process, CAD-CAM polished sintered process, is greater than all other processes due to their rough surfaces. Because the rougher the surface, the heavier the damage, the fatigue damage. So this is two-way ANOVA carried out in order to test whether the surface treatment and the number of cycles influence the contact stress. You can see the p-value for the two is 0, which means the two significantly affect the contact stress. So these are the surface morphologies at different cycle. After one cycle, you can see the the ring cracks, but for the polished sintered is almost not visible. But when we increase the magnification, you can see the ring crack. So now I use the formula shown in the previous slide to calculate the critical load for the cone cracking, and then based on our experiment and material properties for the cone crack, the critical load supposed to be 1,146, which was greater than the maximum load, that is 800. So it is possible that cone cracking did not occur at one cycle. However, using the critical load for the yield, quasi-plastic yield, it was 115 Newton, which was lower than 800. So it means quasi-plastic yield occurs. So you can see for the CAD-CAM sintered, because it has got ring crack and surface defect. For the CAD-CAM polish sintered process, you have only the ring crack. For the CAD-CAM sintered polished, you have also the ring crack and the smeared defect. Okay, for the CAD-CAM sintered glazed, you have what is known as the ring crack, and then because of the formation of the debris, so you can see the pulverized debris. For the CAD-CAM polished sintered glaze, you have the ring crack and the smeared defect. So when the number of cycles was increased to 10 cycles, you can see for the CAD-CAM sintered, you can see the enlargement in the ring crack. So you can see overall ring cracks. You can see the meandering, this is meandering crack part and the micro pulverized debris. For the CAD-CAM polished sintered, you can see overall ring cracks, and you can see the concentric. Now this one has now changed to the ring cracks, now changed to concentric crack part. For the CAD-CAM sintered polish, you can see the ring crack and meandering crack part and smeared surface. For the CAD-CAM sintered glaze, so you can see the ring crack and then ring cracks, and you can see the fretting and then pulverized debris in a wedged, you can see the wedged area. Then for the CAD-CAM polished sintered glaze, you can see the ring crack and then crack part with smeared defect. Now, after 100 cycles, you see the damage the damage is more heavy now. You can see the ring cracks with inner edge shipping, and also micro craters and debris. You can see the hole that is called micro craters. For the CAD-CAM polished sintered process, you see the ring cracks. You can see the fretting and pulverized debris in the wedged area. CAD-CAM sintered and polished, you can see the ring cracks, smearing and fretting, and then pulverized debris in the wedged area. For the CAD-CAM sintered glaze, you can see the ring cracks, then further modification or further leads to radial cracks formation outside the ring. You can see the formation of the radial crack. This is the radial crack forming outside the ring crack. So for the CAD-CAM polished sintered glaze, you can see the ring cracks, then fretting and pulverized debris in a wedged area. Then after the 100 cycles, so you can see here the ring cracks but with edge shipping. can see the large scale edge, shift edge, material removal, and craters. So for the CAD/CAM polished sintered, you can see the one that we propose, the ring cracks with inner shift edge. You can see the shift edge and micro craters. For the CAD/CAM polished sintered, you can see the ring cracks with edge shipping, then fretty debris in the wedged area. CAD/CAM sintered glaze, you can see ring cracks, that is the inner and outer chipped edges. Then you can see a transverse crack coming within the ring cracks. So that's called transverse crack in the wedged area. Then for the CAD/CAM polished sintered glaze, you can see the ring cracks. You can see the continuous and discontinuous ring cracks and the fretting and polymerized debris in the wedged area. Now, finally, at 3,000 cycles, you see the ring cracks. You can see the outer edge shippings. This one has now led to large-scale chipped edge material removal and micro craters. For the proposed manufacturing process, that is CAD/CAM polished sintered, you can see the ring cracks, outer chipped edge, large-scale chipped edge, and material removal and micro craters. Then for the CAD/CAM sinter polish, you can see the ring cracks, inner chipped edge, and the large-scale chipped edge, material removal, and micro craters. Then CAD/CAM sintered glaze, you can see we can see the ring cracks, inner and outer edge shippings, large-scale chipped edge, material removal, and micro craters. Then for the CAD/CAM polished sinter glaze, you can see the ring cracks, inner chipped edges, and then fretting and pulverized debris in a wedged area. So now this is the proposed fatigue mechanism. In a cyclic load, both cone crack and quasi-plastic yield will occur because because of the fluctuation of the load, so they will occur. Then as the load is increased, it will now do what? The cone crack will now extend due to a phenomenon called slow crack growth, while the quasi-plastic will lead to coalescence of micro cracks. So at single load, it will have a deformed surface. When the load is increasing, when the load increases, then there will be deformation along the edge. So because that will now serve as the stress concentration site. So this will further be exacerbated by the surface roughness. So the rougher the surface, the heavier will be the induced damage. So mechanical assisted growth of surface asperities is the proposed fatigue mechanism for the dental restoration that we propose. So in conclusion, CAD/CAM milling followed by polishing and sintering is the proposed fabrication process for lithium disilicate glass ceramic restoration. So the proposed fabrication process can sustain higher maximum contact stress at high cycles and less damage than rougher surfaces. Quasi-plastic is dominant at a single load, and partial cone cracks are formed at higher indentation, while radial and transverse cracks are induced on the roughest surfaces. So ring cracks, fretting, pulverization, micro craters, smearing, wedging, and edge shippings are propagated on all surfaces. So mechanical assisted growth of the surface floor is the proposed fatigue mechanism for all surfaces treated. Thank you very much. So stop.